Alright, so picking up on where we left off on number 41, we had found that the limit as x goes to 2 of x squared minus 3 equal to 1, we had found a width of our box which worked out for epsilon equal to 0.01. The delta that we had chosen in that particular example was 0.002, and we showed that that worked for all x values within that box for this particular value of epsilon. What if we wanted to do it for any value of epsilon? Because that's what we have to do to prove that the limit exists. We have to find for every single value of epsilon an associated value of delta. For every height, we have to find a width. So in order to do that, we do almost all the same exact work as before, even maybe a little bit simpler. So what this means is that we need to find a width of our box, which is what this says. The width of our box being centered about 2 and less than some delta that we choose. And we have to show that that implies that our function f of x and its distance, whatever that value is, its distance away from 1 will be less than any arbitrary value of epsilon, no matter what that value is. So we do the work that we did before, right? We find that that this quantity has to be less than or equal to its individual factors multiplied together in absolute value functions, right? So x squared minus 4 is equal to x plus 2 times x minus 2. And then we take the individual absolute values of each of those factors. And we said that the quantity of the absolute value of x minus 2 we have control over, right? It has to be less than whatever delta that we choose, right? So that can be, so this whole quantity here can be less than the absolute value of x plus 2 times, and we replace the absolute value of x minus 2 with whatever our delta will be. At this point we say, alright, well, let's choose an interval about our limit point. And let's have that interval be between 1 and 3. And you might ask, well, where does that interval come from? As it turns out, to use this little technique, it doesn't matter. It's actually arbitrary. In our previous example, we chose an interval of 0.002. So x was between 0.998 and 2.002, right? Or, excuse me, 1.998 and 2.002. But this trick works for any interval that you choose. You just have to extend the argument just a little bit after this. So let's say that x was between 1 and 3. So the most that the absolute value of x plus 2 could be in the interval of 1 to 3 is 5. So we can replace x plus 2 with 5. Because it can't be any more than that, right? So whatever this whole thing is, it has to be less than, we replace absolute value of x plus 2 with 5, delta. So this here, which is the distance away from our function f of x from 1, has to be less than 5 times whatever we choose our delta to be. And if we want that to be less than some arbitrary epsilon, whatever this might be, then we can set our delta to be equal to epsilon over 5. Now note that this would only work on that arbitrary interval that we chose of 1 to 3. And basically what that means is that it would only work if delta was less than or equal to 1. But what happens if epsilon gets too big? So for example, if epsilon is a little bit bigger than 5, then we get out something that isn't on this interval anymore of 1 to 3. So we start out that we hold on 1 minute. Sorry about that technical issue. So what happens if epsilon gets too big? Well, if epsilon is slightly bigger than 5, or any bigger than 5, then our delta would be greater than epsilon over 5, so it would be greater than 1, and it would invalidate our assumption that that quantity of the absolute value of x plus 2 would have to be less than 5. But we know that a thin box will work for bigger values of epsilon. So if epsilon over 5 gets to be bigger than 1, we can clamp that value of delta to a value of 1 and stop adjusting the width of the box, and only start adjusting it when the epsilon value starts to close in on the point itself. So for example, let's say that we had an epsilon value of 8. So if our epsilon value was 8, right, we would have 8 above and, or excuse me, yes, 8 above our limit point and 8 below our limit point. But we could still just use the value of delta equal to 1, right? Because this, right, our height of the the value of the distance of our function, of any value of our function away from 1, would have to be less than or equal to what we showed before. And if delta was equal to 1, right, then this would have to be less than delta. So we just replace the absolute value of x minus 2 with 1. This would still be less than 5, right? Because our delta, the width of our box was still between 1 and 3, because we just clamped it at that interval. And 5 is less than 8, right? So therefore, we would still be the values of our function would still be within our box. So we would only still be considering these values of the function as opposed to values outside of it. So even though epsilon is is bigger than 5, right? Here is 5 below that. We don't care. And then as epsilon starts to get smaller, that's when our epsilon over 5 would start to kick in. And we would have to start adjusting the width of our box down. So that's where this comes from, right? Our delta equals the minimum of 1 and epsilon over 5. Now if we had chose something different, for example, we chose a different interval, such as, I don't know, instead of 1 on either side of 2, we'd chosen 2 on either side of 2. So let's say x between 0 and, let's say, what do we say, 2, 4, right? On this arbitrary interval. Then the value of x plus 2 would have to be no bigger than 6, right? So then we would go through all of the same derivations, and we would get delta would be equal to either the minimum of 2 or epsilon over 6. All right. In the next couple of this, You only get the hang of this with more practice, so I'm going to post a bunch of problems online and worked out examples for them. Please feel free to either email me or leave a voice message or a text at the supplied addresses that I gave you and contact info. I probably won't get the examples up tonight, but I will get them up very soon. You could probably start working with what I've shown you so far, and hopefully that will work out for you. See you in class on Monday.